Okay, students, welcome to Darasa Online, and today we are going to study physics to the topic of electromagnetism. I'm Cyprian Mgina. Our subtopic, we are looking the electromagnetic induction. We will be able to base onto the factors which really determines an induced EMF in electromagnetic induction. We all know that in 1820, Oersted discovered magnetic field. He did a very simple experiment. Whenever he took a current, passed through a conductor, he was able to prove that the region around a conductor is the region of a magnetic field. It means that there is a magnetic field which is produced whenever a conductor carrying a current. So the region around a conductor carrying a current is the region of a magnetic field. That is a simple experiment which was done by Oersted in 1820, of which later Mr. Faraday tried to do the opposite. He did an experiment in the opposite way by just producing an electric current by the use of the magnetic field. Now, the way on how you can be able to obtain an electric current using a magnetic field is what we call electromagnetic induction. There are several ways on how this can be done. For example, we can be using a simple magnet. A simple magnet which can be used. We could just be able to take a magnet. If you take a magnet and you are taking a magnet, let's say, very near to a conductor, the magnetic field which interacts the coil will just make a coil produce a small induced EMF. And that particular induced current will be able to flow into a certain way. For example, if you are taking, let's say, this to be a coil, if you take this to be a coil of a certain turns, and if this particular coil, let's say, is joined to a sensitive galvanometer G, and a magnet with a north pole and a south pole is just moved towards such particular coil, the magnetic field of this particular magnet, which interacts with this particular coil, will just be able to cause that particular coil have an induced EMF, whose smaller current can just be detected by this particular galvanometer. Now, the process of pushing a magnet towards a coil or withdrawing, receding it away from a coil, will make the magnetic field of a bar magnet interacting a coil to vary. And the induced EMF will only be obtained whenever there is such kind of a variation of an interaction of a magnetic field with a coil. If that variation is no longer existing, there will be no induced EMF. So the induced EMF can be obtained in that way, that the magnetic field that interacts with the coil should have to vary. That variation will be able to produce an induced EMF, and that particular induced EMF can just be detected by such a sensitive galvanometer. Now, that particular induced EMF will be flowing in that particular coil. The direction of the motion of a magnet will dictate the direction of the induced EMF with a smaller current flowing in that particular circuit, such that if the bar magnet were moved towards a coil, if the galvanometer were showing that it is just flowing into this particular direction, whenever you recede a bar magnet away from a coil, the current will just be able to take the opposite course, will be able to flow in an opposite direction, and the galvanometer again will deflect into the other direction. Remember, this is the galvanometer which is zero-centered. So the current will be flowing to a direction depending the interaction of a magnetic field produced by a magnet, for this case, that interacts with that particular coil, which will just be connected to a galvanometer for detection whether there is an induced EMF or not. Now, that particular induced EMF can as well be obtained with the movement of a coil to a stationary magnet. What is very important is just the interaction of a magnetic field with a coil. And this can be achieved as well by moving a coil towards a magnet, move a coil towards a magnet, recede it, move it again. Okay? So that we'll be able to find that the magnetic field of a bar magnet interacts with the coil or made it to vary such that there will be an induced EMF. Something can also happen that, for example, if we are having some two coils, the primary coil, for example, you could have a primary coil like that one, and this one could just be connected, let's say, to a rheostat. This can just be connected to a rheostat and to a cell there and to a switch. And we could have another secondary coil there, very near to it. And this secondary coil can as well be connected to a sensitive galvanometer, G. Now, once you put the switch on, there will be a current flowing through this particular circuit to this particular coil. And whenever this coil flows, according to what I've already said, the experiment which was done by Ostad in 1820, this particular coil carrying a current will be able to produce a magnetic field. So there will be a magnetic field produced here. Now this magnetic field produced all of the way of this particular current, of that particular coil, will interact with the secondary coil. This is the secondary coil. Will interact with the secondary coil. Now, as long as the growth of the magnetic field produced by a primary coil varies, and that variation can just be achieved by using the rheostat. The rheostat can just be decreased or increased. In doing so, the current that is moving to the coil can also be able to increase or to decrease. Increasing or decreasing the current moving in a coil makes the magnetic field that interacts with the secondary coil to vary. And that variation will cause an induced EMF to a secondary coil. And that particular induced EMF can be detected by a galvanometer there. So this is a sensitive galvanometer which can be able to detect even a very small current induced to the secondary coil there. So what is happening here is the variation of the magnetic field. So any particular process which can allow you to have a magnetic field vary, interact, and that particular varying magnetic field interacts with a coil, then there will be an induced EMF in that particular coil, or what we call the secondary coil. And that particular process, or this phenomenon, is really what we call electromagnetic induction, whereby we are having some two laws of the electromagnetic induction. We are having what we call the Faraday law and the Lenz's law. Those are the two laws which really talks about the behavior of the induced current under the process of electromagnetic induction. So we'll just be able to look very quickly those laws, and I believe you have already learned this because this is just like a revision. So we are having the Faraday's law, of which it says that the rate of the induced EMF, that particular induced EMF there, is equal to the rate of change of the magnetic flux. The induced EMF always is just equal to the rate of change of the magnetic flux. And the formula for the Faraday's law says that E is just equal to N d phi dt. The phi there is the magnetic flux. So we are giving the negative sign. The negative sign there dictates the direction of the induced EMF. That if a variation of a magnetic field makes the current to flow in one direction, whenever that magnetic field is varied in an opposite way, the induced current will be able to flow in an opposite direction. So the Faraday's law is based onto this particular case, where the phi there is a electromagnetic flux. Where this phi there is what we call the magnetic flux. And the second one is what we call the Lenz's law. Now, the Lenz's law talks about the direction of the induced EMF in a coil. It says that the induced current or the induced EMF in a circuit, it is always such that it opposes the change which causes it. That always the induced current which will be obtained, let's say, into a secondary coil. That particular induced current, from the basic principle, that particular current will also be able to produce a magnetic field around it. And that particular magnetic field, it will be like to be opposing the change of which it makes that particular induced EMF to be produced. So that's what we call the Lenz's law. So the Lenz's law is really obtained or is referred by a negative sign there, because this EMF is then an induced EMF. So it will be having a direction in a secondary coil where that particular EMF has been induced. So its direction will depend upon the way the particular magnetic field is varied. If it's varied in the way that particular, if it were a magnet, we are just moving towards a coil. If we could be having, let's say, this to be a coil, for example, if the magnet were moved towards it and the current were flowing into this direction, whenever you recede the magnet, the current will be able to flow into the opposite direction. And these are the two laws which guides the process of the electromagnetic induction. Okay, students, as you have already seen, that the direction of the induced EMF is dictated by the Lenz's law. This can as well be determined by the use of what we call the Fleming's right-hand rule, whereby if a conductor moves in a magnetic field perpendicular to itself, then the direction of the induced EMF can as well be obtained by using your right hand by representation of the first three fingers. That if I could have a simple sketch of your right hand, this as your right hand, then we are having something like this. I can take this to be as the thumb and take this to be as the first finger and take this as the second finger, and here I can take this as those other fingers, so that we are having something like this. So if I'm taking this to be the thumb, and this thumb is printed into the direction of the motion of that conductor, and the first finger is printed into the direction of the field, meaning that is the magnetic flux, then the direction of the induced EMF will be printed into the direction of the second finger. So this will be the direction of the induced EMF in that particular conductor. Whenever we are taking the thumb, the first finger and the second finger to be mutually perpendicular, using your right hand as it is here. So this thumb, if this will be representing the direction of the motion, then the first finger will be representing the direction of the field, be perpendicular to the thumb there. Then the direction of the EMF will be taking the direction perpendicular to both of the field and the direction of the motion, that is the direction where the thumb points. So this is what we call the Fleming's right-hand rule. And the direction of that particular induced EMF, as I've already said, really will be dictated by the Lenz's law, as we have already seen here, whenever we are just talking about the two laws of electromagnetic induction. After that, we can now just be able to go and look some particular problems which might take us to some various areas where I can be able to share with you and be able to discuss the way we can just be able to get some problems to some particular challenging areas with regard to an electromagnetic induction. So we can just start with our first question. Our first question says, a student joined a certain conductor to a 12 ohm resistor and having 15 turns, which is made to oscillate across a magnetic flux. If the current of 1.5 ampere is found to be induced across the conductor, now calculate the rate of the change of the magnetic flux. Okay, so we have already seen that particular question. And here we are having such a conductor. We are having this to be a conductor of a coil. It is having 15 turns. So there are so many turns there. Let's take to be 15 turns. Now these particular coils, we are taking to be joined to a certain resistor. We can take this to be joined to a certain resistor, which is 12 ohms. Okay, and the number of turns there. The number of turns there is given to be 15 turns, and the resistance connected to a coil that is 12 ohms. And we are taking that this particular coil is made to oscillate into a magnetic field. Okay, it's made to oscillate across the magnetic field. So I can take the magnetic field to be perpendicular to the board here, so that the field is going inside a board. So the coil is made to move across it. Okay, so it will be varied in this way. It will be interacting with the magnetic field, such that the magnetic field are just moving towards the board. So that is the situation. Now, whenever such kind of a variation is done, the induced current I is just equal to 1.5 ampere. That is the induced current. So we need to calculate the rate of the change of the magnetic flux. So here we really going to rely to the Faraday's law. So from the Faraday's law, we found that E is just equal to minus d phi dt. Okay, and we all know that the EMF. We all know that the EMF E is the one which we need just to find it. Okay, and therefore we could just be able to use this particular data, and therefore we'll just be able to find. We are using the Faraday's law equation to solve this. From the Ohm's law, we know that V is just equal to IR, and this is just like the EMF. And the current I is given, and the resistance R of a coil is known, so that we could be able to find the induced EMF E in terms of volts. And the current I is 1.5 ampere, and the resistance is 12 ohms. And if you calculate, you'll be able to get the induced EMF. That is 12 times 1.5. which is equal to 18. So here we are going to get 18 volts. And having obtained 18 volts, then using this particular expression, it means that what we really needed to determine is the rate of change of the magnetic flux. So the rate of change of the magnetic flux, it is d phi dt. So d phi dt, this will just be equal to the EMF over the number of turns. The negative sign is not so much important to us, because we just need to know the variation of the magnetic field that interacts with the coil. So that the EMF there is 18 volts, and the number of turns, that is 12, so that we could just be able to calculate there and be able to obtain here to be equal to 1.5. So we are going to get the variation now. The variation of the magnetic the variation of the magnetic flux is just equal to 1.5. These are Webers per second. This is the variation of the magnetic flux. You could be able to see what is really very important is to understand those two laws, basically from the Faraday's law. Basically from the Faraday's law. Okay, students, let's go to the second question. The second question goes like this. A square coil of 8 centimeters long has 150 turns with a total resistance of 8 ohms. It is positioned perpendicular to a uniform magnetic field of 0.8 Tesla. If it is then removed very quickly perpendicular with the field to a position of 0 magnetic field in 0.15 seconds, what will be the energy dissipated in a coil? What will be the energy dissipated in a coil? So that is the question. And for this question, we are having such a coil of 8 centimeters long. A square coil of 8 centimeters long. So if it is a square coil, we are having such a square coil of 8 centimeters long. So it's having some several turns there. It will be having some several turns there. So the number of turns, that is 150. And this is 8 centimeters by 8 centimeters. Okay. And the total resistance for this is 80 ohms. Now this is positioned perpendicular to a uniform magnetic field. Now the magnetic field is perpendicular. So we are having a magnetic field crossing through it perpendicular. So the plane of a square coil is perpendicular with the magnetic field. So we are taking this to be the magnetic field B to be perpendicular with a coil. And therefore we are looking we are being given that this particular magnetic field B is of 0.85 Tesla. The magnetic field of a flux density of 0.85 Tesla. Now we are given that this particular coil is just going to be moved very quickly away from the field in a 0.15 seconds. So removing this particular coil will just cause an induced EMF in that particular square coil. So now we now just to determine, after that particular induced EMF is there, now we are being asked to determine what will be the energy that will be dissipated in that particular coil. So that is the situation we are having. That is the situation we are having, and we need now just to solve. The time for removal of this is 0.15 seconds. Okay, so first of all, we need to determine the magnetic flux. The magnetic flux phi always is given by BA cos theta. The angle theta is the angle made between the flux and the plane of a coil. And whenever it's maximum, that is whenever that particular angle is 0, the magnetic flux becomes maximum. And that will happen with this particular situation, because what we need to know is that if I'm having, let's say, if I'm having a magnetic field that is crossing over there, so what we need just to determine is to have a, if we're taking this to be the magnetic field of a flux density B, making an angle theta, to an area A, then we are saying that the magnetic flux becomes the magnetic flux will be maximum whenever this particular field, let's say, is crossing, let's say, in a vertical direction, such that the angle in reference, not this one here, the angle in reference will be equal to this one, such that such that whenever the field is now perpendicular, that's whenever we're having the cos theta is equal to cos 0, then that will just be a maximum magnetic field. So maximum magnetic field is obtained whenever the field is perpendicular with an area. So the plane of the area here is perpendicular to the field. That's when we're having a maximum magnetic flux, which is just equal to B times A. And in this particular magnetic flux, we are multiplying. The B is 0.85, and the area, we are taking this area, which is 0.8 centimeter by 0.8 centimeter. That is 0.08 meter times 0.08 meter. So we are going to get the magnetic flux. And this magnetic flux can just be computed. So if we multiply there, we are having 0.08. We multiply times 0.08 times 0.85. Times 0.85, which is equal to 5.44 10 power negative 3. 5.44 times 10 power negative 3. This is a magnetic flux of which we are measuring this. In Webers. Okay, so that is the magnetic flux. So having obtained this particular magnetic flux, we go back again to our Faraday's law. That from the Faraday's law, we all know that the EMF E induced just equal to N d phi dt. Okay, we just be equal to this much. But the number of turns obtained given there are 150. So we're just going to put 150 there. The rate change of the magnetic flux. Okay. The rate change of the magnetic flux. The magnetic flux is just equal to 5.44 10 power negative 3. We divide it with the time, which is equal to 0.15. So from there, we're just going to get an induced EMF. So we are taking, that is 5.44 10 power negative 3. We multiply by 150. And after that, then we divide by 0.15 seconds. And this gives us 5.44. So the EMF induced will be equal to 5.44 volts. The induced EMF will just be equal to 5.44 volts. Now, we are being asked to determine the actual we need to determine now the actual energy which is going to be dissipated. The actual energy which is going to be dissipated, is just equal to I squared times R times T. Will just be equal to I squared times R times T. And if we compute this, and we substitute the current, the current which is going to, the current which is going to, we needed to substitute this particular value. The EMF just be equal to that much, and we can be able to calculate the current, and that particular current, from the Ohm's law, we know V is equal to IR, so the current I is just be equal to V over R, which is just be equal to the EMF divided by R. The EMF E, the one which is obtained here, to be equal to 5.44 volts, and we divide it by the total resistance, which is 80. So this will give us the current in amperes. And this current in amperes, we could just be able to calculate it. We could just be able to calculate this current in amperes, which will just be equal to 5.44 divided by 80, and 5.44 we divide by 80. This gives us to be equal to 0.068. The current there is 0.068 amperes. This is the induced current, very small, the induced current which can be detected moving in that particular coil. Now that current is the one we're just going to substitute it here. And the resistance R is 80 ohms. And the time T is that particular 0.15 seconds. So that if we substitute the current here, which is 0.068, you square this, times the resistance is 80 ohms, times the time T is just equal to 0.15. If you multiply, you'll be able to get this. If you square 0.068 times 80 times 0.15, we are going to get 0.055. 0.055488. Or simply, we say to be 5. We say to be equal to 5.54 5.548, or rather say 49 times 10 power negative 2. This is the energy which will be measured in joules. So this will be the energy that is dissipated in a coil. And actually this energy can be, you can be able to feel even the temperature of a coil. The coil can just be able to develop some temperature, a heat. That will just be the heat which will just be dissipated in that way. Okay students, let's go to the question number 3. It goes like this. The following figure, there is a figure, I'll be able to show it to you, of a rectangular loop of 8 centimeter by 15 centimeter with a total resistance of 20 ohms is held in a uniform magnetic field of a flux density 4.6 Tesla with its planes perpendicular to the magnetic field which is directed into the plane. If the loop is moved towards the right with a constant velocity of 2 meters per second, A, show that the power needed to move the loop is given by B squared L squared V squared over R, where L is the width of the rectangular loop and B is the magnetic flux density and V is the velocity of the loop. That is A. Part B, compute the value of the power needed to move the loop. So we are having the field, which whereby we are having the field which goes perpendicular to the board. And my loop of that particular size is moved with the particular velocity v. And this loop is a rectangular loop with 8 centimeters to this particular side and 15 centimeters to this particular side. So the magnetic field, what is given here is the resistance. The resistance here, it is 20 ohms. The magnetic field is 4.6 Tesla. And the velocity v of movement is 2 meters per second. So we need to, first of all, to show that the power needed to move this loop is given by that much. So first of all, of what we already derived previously, we all believe that the EMF, that the EMF E, is just equal to B times L times V. The induced EMF E is just equal to B times L times V. But from the Ohm's law, we all know that V, which is equal to the induced EMF, just be equal to IR. But my interest, this EMF E could just be equal to E there, okay? Will just be equal to that much. And we can just be able to solve this. The EMF E is just equal to V from the Ohm's law is just equal to I times R. Such that the current I the current I will just be equal to the induced EMF E over R. And the induced EMF E is just equal to BLV. So this will just be equal to B times L times the velocity V over R. That is the induced current now. Now, having obtained this, then we know that the force in a magnetic field is just equal to the magnetic flux times the current times the length of a conductor. So that we could be able to substitute for this particular current to this particular expression. And that particular force will just take us to B times I. The I is just equal to B times L times V. The I will just be equal to B times L times V over R times L. And the whole of this will make us to obtain the force to be equal to B squared L squared times the velocity V over R. So this is the force. This is the force at which it will just be used to move it. But having obtained this to be the force, then we needed to know the power. Talking about the power, we know it's just equal to the work done times distance. We divide by time. But distance over time, this is velocity. So power actually is just equal to the work done times the velocity times the V. So you can just be able to substitute it there. The power is just equal to work done over time. Work done is just equal to force times distance. We divide by time. But distance over time, this is equal to the velocity. So that the power now, we just multiply the force times the velocity. But this force had already been obtained here. So we substituted this particular expression for the force here. So we're going to get the power to be equal to B squared L squared V over R times the velocity V. So if you write it there, you'll be getting B squared L squared V squared over R. This is equal to the power. And this is an expression which you had been asked to prove to the first part there. And therefore, if we go very quickly to part B, we need to compute the value of the power that is needed to move the loop. So we can be able to substitute now. Now it's a matter of substituting. To obtain the value for the power now, we substitute. The value for B is 4.6. So take 4.6 squared. The length L, it is this length which really interacts with the field whenever it's just moved away from the field, which is over 8 centimeter. And this is 0.08 centimeter, so meters, 0.08 meters squared, we square. And the velocity there is 2 meters per second. The velocity there is 2 meters per second. So this is 2 squared. And we divide with the resistance, which is given there, that is 20 ohms. And if you compute this, you'll be getting 4.6 if you square. You get you're going to get 21.16, and if you square 0.08, you get 6.4 10 power negative 10 power negative 3, and if you square that, the other one is 4. So the whole of this you divide by 20. And if you compute for that case, you are going to get 0.54 divided by 20, 0.5416 divided by 20. So if you divide by 20, you are going to get 0.027, 0.02708. So it means that it is 2.7 1 times 10 power negative 2. This is the power which is measured in watts. So the power will be equal to 2.71 times 10 power negative 2 watts. That is the answer for the question 3. Okay, students, now we are going to see a question for you as a homework. So the question goes like this. A certain magnetic flux made to pass across to a plane of a coil and it's directed into a paper. There is a diagram for this question. Now, this particular coil is made to vary according to that particular relation. That is, magnetic flux is equal to 8t squared plus 5t plus 2. So where phi b is the magnetic flux measured in milliwebers, and t is the time which is measured in seconds. The question comes, A, what is the magnitude of the induced EMF in the loop when the time t is 3 seconds? B, what is the direction of the current through the resistor? My dear students, that is you can be able to see from this particular question, A and B really needs you to understand the Faraday's law and the Lenz's law, to know how and the way induced EMF really depends on, and even the direction. For part B really refers about the direction. So we are having that particular question, and I can be able to give you some hint. I can just be able to give you some hint, and with that particular question, we are given the variation of the magnetic flux across a coil is varying according to this particular expression. It's varying according to this particular expression. 8t squared plus 5t plus 2. And this is measured in milliwebers. So what you need from the Faraday's law, you need to know the rate change of the magnetic flux. I hope you remember the Faraday's law, whereby it says that E is just equal to minus n d phi dt. So you can be able to determine this by differentiating this with respect to t, where t is the time. And finally, you will be able to substitute whenever the t is equal to 3 seconds to obtain the induced EMF E. That is very straight. I hope my dear students, you can be able to do it. And the part B is the direction of the current. If the current goes towards the board like this, if the current goes towards the board like this, and my coil is moving across it, so here I'm having a resistance. Whenever you move the coil away from the field, where do you find the direction of the current through this resistor? This depends upon the Lenz's law. Now we go to the second question as for your homework. The question goes like this. A circular coil of 1,000 turns and a radius of 2 cm is having a total resistance of 10 ohms. The coil is placed in a magnetic field that varies in a uniform rate from 0.04 webers per meter squared to 0 in 0.02 seconds. Determine the following. A, the amount of the charge induced in the coil, and B, determine the amount of the voltage that is induced in the coil. Okay, with this question, we'll just be able to find that you are given a circular coil. And this circular coil is of that particular number of turns. The number of turns of there is 1,000. And the radius of that particular circular coil is given, which is of 2 cm. And it's given that this coil is placed in a magnetic field which varies at that particular uniform rate in that particular time. So we are asked to determine the amount of the charge induced in the coil. But before determining the amount of the charge, you need to determine the amount of the flux. The amount of the flux is just equal to B times A. The flux density times the area, the cross-sectional area of a coil which will be moving across the magnetic field. And for that case, you will know what will be the area A. The area A is just equal to pi times r squared. So you multiply with B, then you'll be able to get the magnetic flux. Having obtained the magnetic flux, whenever you go to part A, the amount of the charge, the amount of the charge for part A, the amount of the charge induced, this will just be equal to, number of turns over the resistance with the change of the magnetic flux. So you should have to look at the final magnetic flux. If you take this to be the final minus the initial magnetic flux, the final was 0. The initial you have just obtained, you have just been given there, and therefore if you substitute there, you'll be able to get the amount of the charge induced into the coil. If you go to part B, as for hint for you, the amount of the voltage induced in the coil, this will be coming from the lenses, will be coming from the Faraday's law, whereby E is just equal to minus dN phi dt, where N are the number of turns which is given there, and you know the d phi dt, the variation of the magnetic, the rate of the change of the magnetic flux. You can eventually be able to obtain the induced EMF E, that is the voltage which is induced into the coil. So this is just a hint for you students, and take this as a homework. I hope you can be able to do it comfortably at home. Thank you, students. I believe with this particular homework, it will take you back for a revision for many more questions which are just very similar to this. So see you next time when we meet again for another part of electromagnetic induction. Thank you.